Now, green flow. Hello and welcome back to differential equations, section 5.3, review of matrices. So, matrix is a rectangular array of numbers. Could be functions, could be other objects, but numbers. So this matrix is called 2 by 3 matrix, and it has 2 rows and 3 columns. It has positions that are row and column. So the first position is A1, 1, and then A, row 1, column 2, and A, row 1, column 3. Then you have A, row 2, column 1, and then A2, 2, and then A2, 3. So we have the positions that we can find within a matrix, so we can locate any value. Matrices are used to store large sets of data, and there are some properties of matrices that you can use to work with these matrices. If you are a computer science major, you should take that course so that you can deal with large matrices like Google search engine, or the image compression like JPEG, or video compression, or audio compression algorithms. They all compress the matrices which store data, digital data. So it ends obviously a lot in terms of application. We just want to take a look at some basic properties of matrices so that we can use them to compute our differential equations. So there's a whole course called linear algebra where for most of the course you deal with matrices. All right, so now what can I do? I can add matrices, add and subtract if matrices are of the same size. We add or subtract same locations. So if I have a square matrix 2, 3, 8, 1, and I want to add to that matrix 4, negative 6, 3, 3, I will add A1, 1 to A1, 1, which gives me 6. 3 minus 6 is negative 3, 8 plus 3 is 11, and 1 plus 3 is 4. So the resulting matrix is again the same size, 2 by 2, and we just add components. For subtraction, we'll do the same thing. So 5, negative 1, negative 6, and 3, and then we subtract 2, 2, 5, 8. 5 minus 2 is 3, negative 1 minus 2 is negative 3, negative 6 minus 5 is negative 11, and 3 minus 8 is negative 5. And that takes care of that matrix. So addition and subtraction is done component-wise. There's no division of matrices, okay? But multiplication is a little bit trickier because for multiplication we have to have a certain rule to hold in order for us to be able to multiply matrices. First of all, we have a scalar multiplication. So if you have, let's say, 3 times the matrix 1, 7, 3, 4, 9, and negative 1, whatever, you will just distribute. So this matrix has 3 rows and 2 columns. You can have them with more rows or more columns. If they have the same number of rows and columns, it's called a square matrix. So this would be 3, 9, 27 going down the first column, and then 21, 12, and -3 going to the second column. So that's a scalar multiplication. But we can multiply matrices as well. Now what's important is that the number of rows matches number of columns. So the number of rows of the first matrix is the number of columns of the second matrix. So let's go with 3, 4, 1, 7, -2, and 2. And this needs to be multiplied by a matrix that has, because we'll be, so the matrix that has the number of rows 2, because the number of columns of the first matrix is 2. So this needs to be multiplied by a matrix, let's say, we can use a square matrix. 1, 2, 3, 4, here, very creative. So what I'm going to do is, this matrix is 3 by 2, and this matrix is 2 by 2, so the answer will be 3 by 2 as well. You pick the first value from the first matrix, which is this one, and the second value from the second matrix, and that's what gives you the answer. Alright, so now how do we multiply? You take this column and you put it on this row. So you would get 3 times 1 plus 4 times 3. And then you move 1 row down. So that will be 1 times plus 7 times 3. And then go 1 more row down. It will be 1 times -2 plus 2 times 3. So those are all the first, and now you move to the second. Again, cycle through all of them. So it's going to be 3 times 2 plus 4 times 4. Then you move 1 row down. 1 times 2 plus 7 times 4. And then you move 1 more row down. It becomes -2 times 2 plus 2 times 4. And now just compute this. So this is 3 plus 12 is 15. And then you have 21, 22. And then you have 6 minus 2 is 4. On the other side, you have 16 and 6 is 22. And then you have 28 and 2 is 30. And you have 8 minus 4 is 4. So what I did is I multiplied the two matrices by going the column from here will distribute here, will distribute here, will distribute here. And then you repeat for the second matrix. So for the second column, the same thing. So matrix multiplication is important because we can now represent systems through matrix multiplication. Look at this. A, B, C, D times X, Y is equal to H, K, whatever. Look at that. This is the way to represent the system. Because when you impose this x and a y to this row, you will get a times x plus b times y is equal to age, which is the top line. You do the same thing, cx plus dy is equal to k. So we can represent the system as a matrix multiplication, which is exactly what our method is going. So there are a few properties. First of all, zero matrix can be of any size and all entries in it will be zeros. So you can have a square matrix 0 0 0 0. You can have, I don't know, 4 zeros this way, like this. Actually, you know what? I'm gonna draw this as a 3, so it doesn't look like the only matrices that we are using are all 2 rows. So now, with this definition, we can talk about properties or matrices. So matrix A plus matrix 0 is the same as matrix 0 plus A, which is A. Commutative, matrix A plus matrix B is matrix B plus matrix A. Remember, they have to be the same size in order for them to add. Well, you can have them any size and they will add. There we go. The next one is distributive property. So as long as the matrices are again of the same size, constant multiplication, which is distribution of a constant, that's also working just fine. And if you have 2 constants added, apparently OBS bugged out, so I'm not sure how much was lost from the stream. So matrix multiplication is not commutative, meaning that you can't do what you do with numbers. 2 times 3 is 6 and 3 times 2 is 6. With matrices it doesn't work because once you make them, right, once you swap them, they might have orders that don't match, and then you can't do the multiplication. See, we said that, remember what we had earlier as an example for multiplication here? Right? So now if you are to swap these matrices, I will write this and I will erase it. So if you are to swap these matrices and put 1 2 3 4 times 3 4 1 7 negative 2 2, well, these 3 cannot go onto these 2 because it doesn't match, right? You go 3 times 1 and then 1 times 2, and then negative 2 has nothing to multiply into. So it's not commutative. You have to be careful about that. Oops. Right. So the next part is the part on determinant of the matrix. You've seen these determinants in Calc 3. You're supposed to know how to deal with them, but let's just take a look at these. So if you have a determinant of the matrix is just the vertical bars. So the matrix should have those brackets, right? That's the matrix. If A, B, C, D would just be the matrix. But if you don't use the square brackets, if you just use the vertical bars like absolute value, that means the determinant of the matrix, which means that you are supposed to compute this, and this is equal to AD minus BC. Now, I usually draw this symbol for students, right? And then that means that you are getting in from this end. And I like this a lot because, look, you have A, and then you are going down into D, but it's A times D. And then there is minus sign over here, the flat, and you go this way now, C times B, and you're done, right? So you just follow that symbol through, and it actually gives you the operations along the way as well. So A times D minus BC would be the determinant of the 2 by 2 matrix. You gotta know this because it's gonna show up a lot. And then 3 by 3 and I'll use P, okay? Because it's the alphabet I know. Goes this way. A, B, C, D, E, F, G, H, P. So what I'm going to do here is, this one is a little bit tricky. You will pick A, so I write A, and when you pick A, then you will delete that row and a column, and you see that now you need to multiply that A into the determinant of EFHP. Then you will move on one to B. Now this is the one, I usually write this one in blood, the minus sign goes there, and then that's B times the determinant of DFGP, and then plus C times the determinant of DEGH. So we take the determinant of 3 by 3 matrix and break it over 3 2 by 2 determinants, and then we solve each one of those. So it's A, we have EP minus HF minus B, DP minus GF, and then plus C, DH minus GE. So this is the determinant for 3 by 3. What's the determinant for 4 by 4? Well, you break 4 by 4 determinant into 4 3 by 3s, and then each one of 3 by 3s into 3 by 3. So after 12 calculations, you end up with the determinant. And then the higher the order, the more annoying it begins, right, until you go crazy. So let's compute the determinant of a matrix. So find the determinant of 1, 3, 7, negative 4. What's the determinant there? the hell? There's a tick over here. What are you doing, little guy? You're so small. They make good pets? Yeah. Get out. Go to them. Yeah. No, it's like every time now. Oh, you have one right there. Same like me. Yeah. See? I know. This one is a horse with a human attached to it. All right, that was a little break for a tick appearance. The what?
Have you seen the evolution of the polo symbol?
No.
So it was like 10 years ago, it was like this, and then now they have one that's like this. Then they're gonna have one that takes up the whole thing of the shirt, and then the next one's just gonna have the horse's head like this.
So technically, it's just zooming in. All right. So what do I have? 1 times -4 minus 7 times 3, which is -4 minus 21 equals to -25. The determinant is -25, and we move along. Great. So if the determinant is not 0, we can use it to find an inverse of a matrix. So A inverse is going to be 1 divided by the determinant of A times D, negative B, negative C, and A. So that's the definition for the inverse. And we can, plug that in and figure out some stuff. So let's see if we can. Let me just find these problems that are already solved in a book. You know all the letters, so you can just read that. Let's find quickly. So let's find the inverse for 2, 1, -3, and 2. So we first find the determinant. I can write it this way. Determinant of A is, just put a vertical bar there, and then you have 2, 1, -3, and 2. Now if this is equal to 0, inverse doesn't exist. But if it's not 0, we can find the inverse. So now what do we have? 4 plus 4 is 8. Great. So the inverse matrix is going to be 1 over 8. 2 times 2 is 4, minus, oh, it's 7, right? Not 8, 7. Make sure you fix this. It's 7. All right, so now we have to shuffle these. So swap, well, 2 and 2, they stay where they are. And then 3 and -1 when you shuffle the C's and B's. And no, they change the signs. So that's -1 and 3. Awesome. So the inverse matrix is 2 over 7, -1 over 7, 3 over 7, and 2 over 7. So that's the inverse matrix. Now, the inverse matrix, what can you do with it? Well, you can solve equations, but let's quickly look into just verify, because it should be clear that if you multiply matrix by its inverse, you should get identity, right? So A times A inverse is 2, 1, negative 3, 2, and that needs to go with 2 times 7, 1 over 7, 3 over 7, and 2 over 7. So now when you multiply these, so these onto those, we would get 4 sevenths plus 3 sevenths is 7 sevenths, so that's 1. And then goes on to this one, you have negative 6 sevenths plus 6 sevenths is 0. Great. Move 1 over, so you get negative 2 sevenths and positive 2 sevenths is 0. Great. And then we have this one and this one, so that's what is this? That's 3 plus 4 is 7 sevenths, so 1. That's identity. This is known as the identity matrix. With these ones on the diagonal. And identity matrix plays the role of number 1 from your regular life. All right? So if you are to multiply matrix A times identity matrix, you will get that matrix A back. So it doesn't change any of the values. How am I thinking? Okay, so that takes care of that. Now, how is this useful for our differential equations? Well, we can transform differential equations into matrices and then use the determinant to solve these systems. So, say you have x1 prime is equal to 4x1 minus 3x2. I could have used x and a y. And then x2 prime is 6x1 minus 7x2. What I can do is I can create the matrix of come on. There we go, of derivatives. And that would be equal to the matrix of coefficients, which is 4, negative 3, 6, and negative 7, times the matrix of x1 and x2. And I can call that system Px. Now we usually put the arrows above the column vectors so that it makes sense. So now I can, actually, you know what, I'm just going to put the notation underneath. So I have dx dt is equal to p times x. So that's the notation. So you can transform any of these systems. Now you know how to solve this, hopefully, using the exponential method of elimination, right? So if you are to solve using a method of elimination, you would get your solutions. So let's see, say solution. Oops. We are not solving this now. I'm just giving you a solution to check. So one of the solutions is x1 of t is equal to 3e to the 2t and 2e to the 2t. So this is one of the solutions. And x2 is equal to e to the negative t, no, sorry, negative 5t, and 3e to the negative 5t. You can check now, using matrix multiplication, you can check if this actually works. Because you can come up with values, well, you will come up, you have them, plug them up there, and see if it works. This will probably be less confusing if I used x and a y than x1, x1, and x2, but such is life. So now overall solution using the principle of superposition would be just add these together. So I hate kind of writing overall solution. Maybe I can just write solution. I'll just put again solution, and I'll write that the x solution for this one in terms of t is c1. Oh, then you can do the combination. Let's just add them. All right, so we'll deal with this when we I can add this later. I'll add this later when it's needed. Don't worry about it now. Is there anything else that I want to add? So we have the superposition. Yeah, okay. I think that's it. That's it for now. So let's go with 5.4. The eigenvalue method for homogeneous systems.